y'all, welcome back to our kitchen. Last week we made a delicious, absolutely scrumptious chicken pot pie. But this week we're doing a little something different. It's a special thing for you little chemists out there. This week we're going to be making wintergreen oil. It's a chemical that just smells delicious, like an alpine breeze in Switzerland. So we're going to need some DCM, dichloromethane, or as I like to call it, liquid cancer. We're going to need some 0.8 sodium bicarbonate, a base. Going to need some methanol. And finally, salicylic acid, or SA, as well as sulfuric acid. And just an extra one just in case. Also, our cooking utensils this week, we're going to need a hot plate, a GCMS and NMR machine, and a reflux condenser. Alright, so to start off, we're going to take our beaker here. This is going to be what's holding all our chemicals together. And we're going to start off with about 2 grams of salicylic acid. So, you know what they say, cooking isn't an exact science. So we're just going to take 2 grams, pour it into our beaker. It's about 2 grams. And then we're going to take our methanol. We're going to add about 10 milliliters of methanol to our solution. All right, that's 10 milliliters. And then we're going to add 6 drops of sulfuric acid into our beaker. All right, that should be good. All right, and now we're going to check the pH of the solution because we want it to be around 2, okay? So 2 is the pH we should be looking for. All right, that looks to be around 2. So now to explain our reaction pathway, I'm going to hand this over to my assistant, Penelope.
Sulfuric acid, an acid catalyst, creates a new pathway for the reaction by altering the stability of the reactants and products in the slow step. The change in enthalpy of the slow step is lowered through the addition or elimination of charges. More charge is added to the reactant, decreasing stability and increasing its potential energy, and a charge is removed from the product, increasing stability and decreasing its potential energy. Lowering delta H causes the activation energy to be lowered, essentially increasing the rate of the slow step and overall reaction. Increasing temperature will increase the average kinetic energy of the molecules and cause more collisions to occur, increasing both the forward and backward rates. According to the speed distribution curve, heating the reaction will increase the amount of molecules with enough energy to overcome the energetic barrier and collide, increasing the rate. Using an acid catalyst and running it on reflux will increase the product yield in the limited amount of time we have in lab.
Alright, so now that we've let this reflux machine run for a little while, we've refluxed the heck out of it, pardon my language. I'm going to turn this over to my good friend Giuseppe, who's going to help us run a liquid-to-liquid pH extraction. Buongiorno! My name is Giuseppe. I'm going to be running our liquid-to-liquid pH extraction today. So, how do we do this? We are going to take 1 centrifuge stool. We are going to take the product that we got from our reflux machine. Thank you, very big thank you to Martha Stewart for running that. We're going to take it and carefully pour it into our centrifuge stool. Make sure not to spill. Then, to complete our liquid-to-liquid pH extraction, we are going to use some DCM. We're going to use about 10 milliliters DCM. Alright, 10 milliliters DCM. Then we're going to add our base, 0.8 molar sodium bicarbonate. We're also going to add 10 milliliters. So once we add that, we are ready to do our pH extraction. So we are going to shake it to make sure that everything mixes together and reacts. So, why are we doing this? What's the point of this? What we are doing is we are going to draw out all the impurities like water, methanol, and salicylic acid into the bottom layer of the organic, or the aqueous layer. Forgive me, English no good. And our top layer is going to be organic, our DCM, and it's going to contain wintergreen oil. To explain further, we have our wonderful assistant Penelope explaining.
During our pH extraction, we use pHs of 2 and 8 due to the predominant forms that would be in each layer at different pHs. To help determine the predominant forms in each layer, we use their pKa's and their following percent concentration versus pH plots. When the pH is 2 in the organic layer, there should be neutral methyl salicylate and 89.28% of neutral SA. In the aqueous layer, there should be neutral methanol, 50% hydrogen sulfate, hydronium, carbonic acid, 50% conjugate base of hydrogen sulfate, and 10.72% conjugate base of SA. At a pH of 8 in the organic layer, there should be 93.7% methyl salicylate after 1 sodium bicarbonate wash. In the aqueous layer, there should be methanol, hydroxide, conjugate base of SA, second conjugate base of sulfuric acid, bicarbonate, and 6.3% conjugate base of methyl salicylate. Ideally, the methyl salicylate should have been isolated in the organic layer, but neutral SA may still remain, so we'll have to do another sodium bicarbonate wash. Adding a strong base will decrease the concentration of H3O plus ions, increasing the rate of the forward process more than the backward, leading to the consumption of neutral SA and the formation of more products, which includes the conjugate base of SA. The conjugate base of SA is more soluble in the aqueous layer than the organic, so more SA will be drawn out of the DCM.
Oh, hello. So once we have done our pH extraction, we should have just wintergreen oil in the organic layer and all the other impurities in the aqueous layer. So now that we've done that, we can take our 50 milliliter beaker and take off the organic layer, which should consist of only DCM and wintergreen oil. So normally you pipette off the top layer, but Giuseppe professional, he just pour off. Perfect. So once we do that, we should check the pH of the layer that we pipetted off, so we know which one we pipetted off. Make sure that you don't accidentally take aqueous layer at full. So put that over there, that's the aqueous layer, we no longer need it. So at this point, take a deep breath of the organic layer and smell for the wintergreen oil and cancer. Alright, yeah, definitely wintergreen oil in there. So now we take our 50 milliliter beaker and we're going to boil it. Like that. And once all the DCM boils off, we will be left with pure wintergreen oil. So now that we're done, we should take our organic layer, which no longer has DCM and is just wintergreen oil. We should take this and measure it, just so we know that what our final yield product is. So now that we know how much weight we have of wintergreen oil, we can run some diagnostic tests on it. So specifically, we are going to be running GCMS and NMR. So we're just going to put it in the machine. And now we should hopefully generate some numbers out of this.
After running GCMS and NMR, we concluded that we successfully synthesized wintergreen oil but unsuccessfully isolated it. We successfully synthesized wintergreen oil because in an NMR standard, distinct peaks of methyl salicylate are a peak at 3.95 ppm and a peak at 10.73 ppm. In our NMR, we had several peaks from different molecules. However, we had a single peak at 3.92 ppm, meaning that methyl salicylate was present in our unknown sample. In our GCMS, peak 1 had a molar mass of 152 grams per mole with ion fragments of 39 grams per mole, 92 grams per mole, and 120 grams per mole. Methyl salicylate was the only molecule in our reaction with a molar mass of 152 grams per mole, and when we analyzed the ion fragments of it, it was identical to the mass spectrums. We unsuccessfully isolated wintergreen oil because peaks that didn't correspond to methyl salicylate were present in both our GCMS and NMR. In our NMR, peaks not corresponding to methyl salicylate was the B peak, the CH2 group on DCM, at 5.27 ppm, and the D peak, the methyl group on methanol, at 3.5 ppm. The A peak in overlap signal at 7.17 ppm, corresponding to the aromatic hydrogens on both SA and methyl salicylate. If only methyl salicylate were present, only the A peak, C peak, and an additional peak at 10.73 ppm would be present. In our GCMS, while peaks 3, 4, and 5 were error or disturbances, which was determined due to the unrealistically high molar masses and random ion fragments, peak 2 represented SA since it had a molar mass of 138 grams per mole and ion fragments of 39 grams per mole, 92 grams per mole, and 120 grams per mole, perfectly matching the molecule of SA. If wintergreen were isolated, peak 2 wouldn't have been present and only peak 1 would have been present. After analyzing our GCMS, our peak 1, which was wintergreen, had a 13.36 purity, and after doing some calculations, we had a product yield of 15%.
What do you mean it's not pure? I did everything right, I followed the instructions, I listened, I read. Giuseppe career is over. I'm a failed chef. Got nothing left anymore. Doing this next week when we make chicken Alfredo.